Hello everyone, my name is Angel Garcia,
And my name is Kevin Chen.
and we will be presenting the fundamental aspects that we incorporated in our rocketry project. These aspects will include the design, engineering, testing, and analysis of our rocket and how successful our experiment was. The goal of our project was to send our scratch-built rocket to the highest possible altitude and return the payload, which included the altimeter, accelerometer, camera, and raw egg, safely back to the Earth's surface. While designing our rocket, we had to keep certain parameters in mind, such as weight, drag, structural integrity, and aerodynamics. The rocket was also built from a cardboard tube, balsa wood fins, and plastic nose cone capsule to conceal and protect the egg during flight. An E-motor was also used to propel our rocket into the air. As a result, in keeping all parameters in mind, we decided to design our rocket with a shorter fuselage to reduce drag and weight, and we also included large tapered fins to increase stability and aerodynamics. All of these designs were brought to life by hand building our fuselage, parachute, and payload mounts, while also utilizing the CAD software to laser cut our fins for precision accuracy. Our fins measured 3.5 inches in width and 1.75 inches in height. Our camera and two altimeters were also held with a styrofoam mold, so they could be easily inserted and held tightly during flight. Unfortunately, our video couldn't be used because our parachute detached from the payload section of the rocket, causing the camera to shift inside its mount and blocking its view from outside the rocket. So we had to use someone else's rocket video.
The static test shows thrust versus time in a similar motor. You can see that the motor provides a significant amount of thrust for 2 seconds before the propellant runs out. This compares rather well to our altitude versus time graph. That graph shows the altitude was concave up or was accelerating upwards for about 2 seconds, indicating that the thrust element was the primary vertical force. As the propellant burns out, the altitude becomes concave down, showing that gravity is now the primary vertical force, as the rocket is still climbing but at a slower rate. The static test also shows that the ejection charge occurs approximately 8 seconds after ignition, which would correlate to the rocket's apogee, indicating the parachute deployed at a rather optimal time. Unfortunately, we did not get any footage from the camera. However, the altimeter was able to record some data. The maximum altitude of our rocket was 858 feet above ground level. Unfortunately, the structural integrity of the rocket was a mixed bag. The knot that tied the shock cord to the payload section unraveled, releasing the payload section into a free fall. As a result, our egg broke on impact. The parachute, however, did deploy successfully for the main body and significantly reduced the descent rate. Our results taught us a few things. First of all, we probably underestimated the force of the ejection charge and should have tightened the shock cord more. Second, despite our rocket had unusually large fins, our apogee was actually rather comparable to other groups. This might have been due to our shorter fuselage and the fact we spent a lot of effort streamlining the airfoil. Considering that, it will be interesting to see how a significantly smaller stabilizer would increase the apogee.